All righty, let's go ahead and get started. So the plan for today is to have our exam review. Exam 2 will be on Tuesday next week. And just like the first exam, it'll be held online or like a take-home test. It'll be posted Tuesday morning. You'll have the full day to work on it. Just as before, there'll be a PDF uploaded to Canvas. You download the PDF, that's the test. You work out the problems. Of course, show all your work because that's how I will be able to give partial credit when necessary. And also it'll be the way I can determine whether you did the work or whether someone else did. Also, box your answers. That helps me, of course, figure out what your answer is versus what the work is and things like this. So work out the answers, of course, have a calculator. These are going to be all calculation style questions, just as before. So not only do you have to set up the problems, but of course you have to be able to get the answer too. When it comes to the answers, generally speaking, the rule I like to use is to give about 2 or 3 decimal places. That's usually more than sufficient to have the answers be accurate. We don't have to follow the true significant figure rules for what we're doing. Of course, if we're doing something more professionally, then we'd have to follow the rules of significant figures, and likely you have to do that in other classes like chemistry and whatnot. But for our purposes, since I'm trying to focus more on the physics and less on all the other formal details of things, I just choose not to worry so much about that. So 2 or 3 decimal places is usually good. That makes sure that not too much rounding is being done and all of that. So answers will match up fairly close. Of course, if there are questions where you could either have a fraction or a decimal, you can have either one. So don't be afraid if the answer is 1/4 or 0.25, you can have either one. It doesn't matter to me how you write it because I understand both, of course. But certainly have a calculator because you're going to need it to actually get the answers for a lot of the problems you're doing. Just as before, the test will be made out as if this is the normal in-class, hour and 15-minute test that you would generally be having. I'm not going to take advantage of the fact that this is in fact online and make it twice or 3 times as long or much more complicated or anything like that. It's just like the test you would be taking if we were doing it in class. And so likely you can expect somewhere around 6 or 7 problems. Okay, I've usually found that's a good number of questions for the type of material we do, where the average person can certainly finish in enough time comfortably. It's not a big rush. So you can expect about 6 or 7 questions. As I said, they're all calculation questions, so you're actually getting numbers as your answers and things like this. Once you've completed the test, then you upload it back onto Canvas. There's a submission button as usual, and you'd submit it back by 11:59 p.m. Okay, so that's the deadline. And again, I highly recommend that you don't wait till 11:59 to try to submit it, because usually some weird technical issue comes up and then I get an email the next day or a few hours later saying, hey, I tried to submit it, but it wouldn't let me. Well, if that comes in after the deadline, how in the world do I know you actually attempted to submit it before the deadline? And it's not just that you ran out of time or whatever. So you have the full day. Try to submit it early. That way, if there is an issue, you can email me before the deadline And at least that alleviates any pressure on your part about whether I think you're trying to get away with something or not, kind of a thing. So try to submit as early as you can. But like I said, you have the full day. It'll close at 11:59 p.m. If you have questions about the test, if you're confused about something, or maybe the picture, you don't see the numbers too well, or whatever the case is, as usual, send me an email and I will do my best to explain whatever the confusion might be. The only things that I can't do or I can't answer are the types of questions like, hey, can you look at my number 3 and see if it's correct? Or, I don't know if I'm doing this right, can you tell me? No, I can't. This is a test. This isn't homework. This isn't just practice. And it's supposed to test your ability to independently work the problems. Now, if there's some wording in the question that you're confused about, or as I said, maybe there's a drawing and you don't know if it's a 7 or a 2 or things like that, obviously, I'm more than happy to answer those types of questions, because I want to make sure you understand the question you're trying to answer. I'm not trying to trick you. I'm not trying to make it harder than it's supposed to be. I just want to have basic fundamental questions on the material and see if you can answer them. So if there are issues about the test questions or anything like that, send me an email and I'll try to respond as quick as I can. So that's the formality of the test. As I said, you've already had one test in this class, so whether you've had me before or not, you now know what the tests look like, how they're run, and this test will be no different. Same thing, it's just that the topics are different. And speaking of that, of course, what are the topics that will be on this test? Well, the test is on everything since our last test. So it's not cumulative. The final exam is cumulative, but each one of our normal exams is not cumulative. It's just on the material we've covered for that exam. And so that basically means we're talking about fluids. And with fluids, we had several kind of mini topics that popped up. The first was Bernoulli. So with Bernoulli, we had the big equation, which was P1 plus 1/2 rho V1 squared plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. Okay. And this is basically a statement that all of the ways the pressure can change in a fluid from one spot is constant along all other spots. So if you have a pipe system and you know information about the water flowing through the pipe at this location, then if you look at this other location, the total pressure of the system is going to be the same. Now, what can change is how the pressure is allocated. You have it in the velocity term. Do you have it in the fact that the pipe went up to the second floor or went down to the basement? Things like that. Just like with conservation of energy, where you have the total energy is conserved. So at this location, the total energy is the same as at that location. However, how the energy is allocated, some of it in kinetic, some of it in different forms of potential, can change throughout the problem, but the total energy doesn't change. Same thing here. It's exactly the same type of thing. And of course, we know that there are going to be different problems where maybe we don't need all of the terms. So if you have a pipe system where the pipe doesn't change height, then the term with height in it just cancels out. You don't need it. Or if you have a pipe system where the pipe doesn't change size, it doesn't constrict or expand or anything, then you don't need to worry about the terms with velocity. But the general problem will have all of the types of changes, and so you'd need all the terms. Along with this, of course, was a second equation called continuity. which helps you use Bernoulli's equation when you have the pipe changing size. Because as I said, there's a relationship here about the size of the pipe and the speed, the velocity term for this equation. Well, how are they related? They're related by the fact that when you constrict the pipe with water flowing through the system, the volume flow rate, which is how much water is flowing through the pipe per second, is constant. And in order for that to happen, when you change how big the pipe is, the opening, if you make the opening smaller, you would think you'd get less water going through. Well, the way to get the same amount of water going through is the speed of the fluid must change. The water must speed up in the smaller section to get the same amount of water through per second as it was doing in the big section. And that's the continuity equation, shows this relationship. It says that the size of the pipe in one location, the area, times the speed of the fluid flowing in that area is the same as the size of the pipe in another area times the velocity of the fluid in that area. Okay. And of course, we know that area here means the area of the opening of the pipe, how big the opening of the pipe is, and that area is just pi r squared. Okay, because we're talking about nice cylindrical pipes. We're not talking about other types of shapes of pipes like a square or what's called a parallel pipette shaped pipe or something weird like that. Here we're talking about a cylindrical pipe, so the opening is a circle. And so the area of that circle is pi r squared. And so the combination of these two equations allows you to solve a great number of problems that deal with things like pipe systems. Fluid flowing through a pipe, the pipe constricts, goes up to the second floor to the shower, and you want to know how the pressure changes. Well, you'd make use of these two equations. You'd set up Bernoulli. You'd need to know probably about the velocity in the second part, up where the shower is located. And in order to get that, you use continuity. That gives you the second velocity. You can now plug that number into Bernoulli, and now you can solve for the change in pressure. So that was the first big topic under fluids. Bernoulli's equation, along with continuity to help out, allows you to solve fluid pipe systems. Then another topic we have is how the pressure acting on an object changes as it goes down in depth inside of a fluid. And so that's the pressure depth relationship. And what it says is quite easy. The change in the pressure on an object, that is how much more pressure it's going to feel, P, is given by what kind of fluid is the object in, that's rho, the density of the fluid, times gravity, 9.8, times h, which is the depth that you went down. So if this is a diver who dives down 100 meters under the surface of a lake or the ocean or whatever, and you want to know how much extra pressure will that diver feel because he's down under the water, this is a type of equation you would use. Now, this brings to mind, by the way, I keep using the fact that this is the change in pressure because there's a concept which is gauge pressure. Gauge pressure is exactly that. It is the fact that everything feels atmospheric pressure. Just being here on Earth, in the atmosphere of the Earth, we already have a fluid applying a pressure to us. That's the atmosphere. The air around us is pushing on us, creating a pressure on us. So everything already feels that pressure. But then, since everything feels this pressure, we could just ignore it because everything feels it. It's not like one object will feel it and another won't, so it's important. If everything feels it, then we just call that like our 0 point. That's where our pressure starts. It starts at this pressure and we change it by some amount. That's what gauge pressure is. Absolute pressure is accounting for the fact that you already have atmospheric pressure. So absolute pressure means what's the total pressure acting on an object? That would be how much pressure is due to the atmosphere plus how much extra it feels because of whatever it is you did. And so the gauge pressure, if we want to count this as an equation, gauge pressure is going to be the absolute pressure, which is the total pressure acting on the system, including atmospheric, minus the atmospheric pressure. And the atmospheric pressure is just a constant. It's a number, 1.01 times 10 to the fifth, or whatever it is. It's something that would be given on a test if you need it. But this is where reading the question given on the problem would become important. When I give you a question, you have to ask yourself, what am I being asked for? Am I being asked to find the total pressure acting on something? Or just how does the pressure change? And so the rule we're going to use, that we're going to go by for this class, this is not the rule of the world, it's not the standard rule, this is just the rule we're going to use, is always assume I'm asking for the gauge pressure unless the question specifically says something like, what's the absolute pressure or what's the total pressure? If I don't ask one of those two, then you just assume I just want to know the gauge pressure. How does it change? And that's, for instance, the pressure depth equation sitting there, that's gauge pressure. Because nowhere in that equation do you know about the atmospheric pressure. But if I ask, a diver dives down 100 meters into the water, what's the absolute pressure he feels, or what's the total pressure he feels, then what you would have to do is you would first calculate the rho GH, that would be gauge, and then add in atmospheric pressure. When you add the atmospheric pressure to that number, now you have the total pressure or the absolute pressure. Okay, so just note that, because of course that's how the real world works. When you go, as I used this example before, you go pump up a bicycle tire, you plug in the pump, and the little gauge that's on the pump that tells you how much pressure is in the tire would say 0 if it's empty. But of course, we know the actual pressure on the tire is not 0 because the atmosphere is there pushing on it. But the gauge just says, look, I don't care about atmospheric pressure. Everything feels it. So the fact that it's just as atmospheric pressure means it's basically nothing. It's 0 pressure. And you need to add more pressure to it. And what you add to it is the gauge pressure. So when you're doing stuff in the real world, you're always working with gauge pressure. But it is important if you're a scientist, of course, and you're doing experiments, or the fact that if you go up on a mountain, you're at a much taller altitude, the pressure acting on an object on top of a mountain is less because the atmospheric pressure is less up there. And there's a lot of effects that come from this. So atmospheric pressure, or absolute pressure actually, is important for certain things. So we still have to know about it. But for most normal purposes in our everyday lives, we only deal with gauge pressure. And so that's why I'm using the rule. If I give you a question, calculate the pressure on something, you assume it's gauge pressure, unless the question specifically says, tell me the absolute pressure, or tell me the total pressure. All right, so that's the next kind of little topic. Object goes under the water, a certain distance, what kind of pressure will it feel? Then we have something called the apparent weight. And the apparent weight is the phenomenon whereby an object, when it's in a fluid, will experience what's called a buoyant force. That is, and we know why there's a buoyant force. If you remember the picture, an object is underwater, the object has a certain size, And so the top of the object is at a different depth than the bottom, which means the bottom of the object has more pressure than the top. So if the bottom feels more pressure than the top, there's more force pushing up on the object than there is pushing down on the object. And so there's some extra force trying to lift the object up. Sometimes it's enough to make it float. Sometimes it's not, and thus the object sinks. But whatever it is, there is some buoyant force. And so since there's a buoyant force on an object while it's in a fluid, if you go weigh the object, the weight scale doesn't know there's a buoyant force. It just says, what do I feel? I feel this thing feels this heavy. And how it feels is called the apparent weight. And apparent weight is very similar to like a gauge pressure type equation. It says it's the true weight of the object, which is mg, mass times gravity, minus the buoyant force, which is acting on the object. And so the more buoyant force there is, the less heavy the object would feel. And in fact, if the object floats, that means the buoyant force is the same as the true weight or more, and thus the apparent weight goes to zero or becomes negative, let's say. So that's another thing you may need to know. Maybe you're a treasure hunter and you want to use a robotic submarine to lift up a sunken treasure chest, and you need to design this robotic submarine to be able to lift the treasure chest, so you need to know how heavy is the treasure. But since it's not just there on the surface of the earth, it's underwater, you know that the weight is not just the weight, it's the apparent weight. The robotic submarine won't feel mg, it's going to feel the apparent weight of the sunken treasure. And so you'd have to do a calculation like this, let's say, to be able to determine what the submarine would feel. And then finally, I believe finally, the last kind of set of topics is what's called Archimedes. Archimedes Principle is actually a set of relationships that are all kind of interconnected. And they deal with the buoyant force, usually, that's acting on an object. When you place an object in water, let's say, I'm going to use water as the stand-in for the term fluid, because it's comfortable. You put an object in water, well, first of all, the water has to move out of the way to make room for the object. And so because of that, what you would see if this is a glass of water or a bathtub that you get into, you'll see that the water level rises higher than it was before you got into the bathtub. Again, obviously, it's because the water had to move to make room for your body. And so the water level rises to make room. And so the first relationship we know is that the volume of the water displaced by an object, and displaced just means how much is moved, it must be the same as the volume of the object that was placed into the water. Because it's the object that made the water level rise. So of course, the water level is going to rise by the same amount as the size of the object. It's not going to be more than the object, because why did it have to move that much? And it's not going to move less because it has to make room for the whole object. So that's the first little relationship. If the water level rises, the volume of that rise must be the same as the volume of the object. Another relationship for Archimedes' principle tells you that if you take the water that was displaced, so let's say we set up an experiment with the bathtub, we fill the bathtub all the way to the tip top, and then you got in the bathtub. Well, the water is going to overflow, and let's say all that water is collected. So they collect all the water that overflowed over the top of the bathtub when you got in, and they now have that in a bucket. It turns out that if you weigh the bucket of water that was displaced, so the weight of the water displaced, it happens to be the same as the force which is being applied to you, which is called the buoyant force. So when an ice cube is placed into water, the water level rises. If you take how much water was displaced and you weigh it, that amount of weight, that amount of force is what the ice cube is feeling as a buoyant force. It's the same amount. But sometimes this isn't very helpful because we don't necessarily know what the weight of the water displaced is or things like this. We know physical characteristics. So we know things like the density of the water or the volume, of course, from the first equation. And so what people do is they just replace weight of the water displaced. We know weight is mg, and we also know rho is m over v, right? Mass over volume. So if what I can do is replace weight with mg. So mg for the fluid is the buoyant force. But then I don't know what the mass of the fluid is, so I use the density equation to say mass is density times volume of the fluid. And so now what we get is the main equation, the density of the fluid, oops, wrong color. The density of the fluid times the volume of the fluid times g. That's mass times gravity, which is the weight, must be the same as the buoyant force. This is more helpful because now what we have are the actual physical characteristics, things we can measure. I don't necessarily know the weight, but I do know the density of the water, and I do know how much water was moved out of the way, because maybe I know the volume of the object. So that can give me the mass. Mass times gravity gives me the weight, and now I have the weight of the water displaced as the buoyant force. And then sometimes this is rewritten because, like I said, we may not know the volume of the fluid, but we may know the volume of the object. From the first equation, they're the same thing. So I could say this is the same as density of the fluid, volume of the object, times gravity is the buoyant force. And so it's this combination of relationships that I'm going to refer to as Archimedes Principle. Okay, and you're given questions. You could be given a question like an object, a steel ball is placed underwater. The steel ball has a radius of whatever, and it's made of this metal, which has a density of this. What would be its apparent weight? Okay, that's a basic Archimedes question. What I would do is I would use the apparent weight equation, which needs the true weight, and it needs the buoyant force. Right? That's what that equation says. True weight, that's fine. That's just mg. Of course, if I don't know m, but I do know the density, then it's rho times v times g. So I could get the true weight. There it is, a number. Now I need a buoyant force. Well, how in the world do I know what the buoyant force is? That's where Archimedes comes in. I calculate the buoyant force using Archimedes' principle. And now I know the true weight. I know the buoyant force. And now I could use my apparent weight equation to solve the problem. So that's where Archimedes type of things comes in. Then there is actually one last relationship we need to know. And that is what I like to refer to as the percent submerged relationship. And this goes like this. Say you have an object that's in water and it's floating there. And of course, if this is a ship, a ship doesn't float literally on the top surface of the water. Some of the ship is under the water, but most of the ship is above the water. And that's what we call floating. And we may want to know something about the ship. Maybe we want to determine its weight. Maybe we want to determine what it's made of, or whatever it is, or we want to theoretically see would it float. Well, this type of relationship would tell us. What the relationship says is that the percent or fraction of the object submerged under the surface must be equal to the density of the object over the density of the fluid. So here you can have a question like a boat is placed in the water and you notice that 2/3 of the boat is above the water. What is the density of the boat? Well, that is where this type of equation comes in. You say, well, 2/3 of the boat is above the water. That means 1/3 is below the water. So the percent submerged is 1/3. So I say 1/3 is equal to the density of the boat, which is what I want, divided by the density of the water, which is 1,000 or whatever liquid it is we're talking about. And then you just solve it for the density of the boat. And so this is a very, very useful relationship that makes what would be an extremely complicated mess of a calculation to calculate the density of a boat, which is made up of all sorts of materials, all sorts of weird shapes. You got chairs, desks, the floors, the wall, all sorts of stuff, all made of different materials. And somehow we have to calculate the density of that thing. Well, thankfully, we can avoid all the complication if we know this relationship. If we just look at how it floats on the water, we figure out how much is under the water. That's the percent submerged. And we can calculate the density. And I believe that's all of the topics. So it's a whole bunch of little topics. We got Bernoulli and continuity is like one topic here. You got the pressure depth relationship and gauge pressure kind of go along together. And then you've got the apparent weight and Archimedes kind of go together as a topic. And then little bitty submerged there is its own little topic. And so it's kind of like you have 4 subtopics under fluids. So you say, okay, well, I expect 6 or 7 questions. So at least one of each, and some of them have 2 problems each, something like that. So between 1 and 2 problems for each one of these kind of categories is what you can expect. Now, some of them are really quick, like the percent submerged type of question is very fast. You could do that in 10 seconds. And so maybe I could have 2 or 3 of those because although it's a question, it's a really basic question. There's not much to it. Whereas something like Bernoulli is kind of a complicated thing because you have the main equation of Bernoulli and then a secondary equation, continuity, you also have to work on at the same time. And so that type of question takes a little more time. But anyway, those are the topics. That's what you can expect to see on the test. Obviously, as you study, the way you should study is number 1, look back at the homework problems that are posted or that have been submitted. And the practice problems that are on Canvas, the solutions are there as well. So just go over them, see the types of questions, the wording, the language, because that's what the typical test question is going to look like as well. Also, any example problems we've been doing in class, rework those problems, see if you can get the same answer. Obviously, I post all of these Zoom videos as well as these notes that I'm taking here. I post them on Canvas, so you can always go back. The videos are on YouTube, so they're streaming. You don't have to download the videos. Just go back, look for some examples that were done, watch the examples and see if you can answer the question, and then check to see what I do and see if you get the same answer. So with those things, you'll be fine. If you can handle the example problems and the homework problems, then anything on the test will be of that type for sure. Any questions about this test? All right. Well, just as a reminder, believe there is the homework for Archimedes is on Canvas. I have it due Friday, tomorrow. That way you can have it worked out and I can grade it before we get to the test day. That's why I made it Friday instead of next week, to give me time to be able to grade it. So definitely work on it. It was posted a few days ago, but I think it's 2 questions, a percent submerged question and an Archimedes question. So be sure you're working on that if you have not already submitted it. And just look back at these practice problems and practice them. Get out a blank sheet of paper and try to work these problems, because that's what the problems will look like on the exam. So if you could do the problems that are on the practice page or what we've been doing in class, you should get 100 on the test. It's the same stuff, which would be nice, because when people get 100 on a test, it makes grading a lot easier for me. And I'm always appreciative of that, for sure. So anyway, if you have no questions, you are free to go and enjoy your weekend. Be sure to email me if you do have questions that pop up as you're studying. I'll be happy to look over what you're doing and let you know if you're doing something wrong or whatever. But I will email you again when the test is posted for Tuesday to remind you to get to work on it. Other than that, we're done for the day.
Thank you. Have a good weekend.